studied physics and geophysics at the University of Lancaster. In 1976, inspired by NASA's missions to Mars and the prospect of the Voyager mission, she moved to the United States for graduate study at MIT. Her 1981 PhD thesis involved analysis of data from the Voyager plasma science experiment in Jupiter's giant magnetosphere. She spent 1982 to 1987 as a postdoctoral researcher in space physics at Imperial College of London. The Voyager flybys of Uranus and Neptune brought her back to the U.S., and she joined the faculty of the University of Colorado Boulder in 1989. She was professor of astrophysical and planetary sciences until 2015, when she chose to focus on NASA's New Horizons and Juno missions. She remains a research scientist at the Laboratory of Atmospheric and Space Physics. In addition to the Voyager mission, Dr. Bagenal has been on the science teams of the Galileo mission to Jupiter, which we had you present on earlier. It was wonderful. And the Deep Space One mission to Comet Borrelly. She edited Jupiter, Planet, Satellites, and Magnetosphere through the Cambridge University Press in 2004. And she's on the plasma teams of the first two New Frontiers missions. The New Horizon mission that, after a 9.5-year flight, flew past Pluto on July 14, 2015, and Juno that went into orbit over the poles of Jupiter in 2016. Thank you, Fran.
Sure. Okay, thank you. It's a great pleasure to be back here. I really love talking to astronomy clubs. It's one of my favorite things. And I've been here before, and I remember a lot of you, met a lot of you before. Let me just mention something about the sun. You're talking about the sunspots slowly beginning to come back. Big debates in the solar community about what the next cycle is going to be like. Probably wimpy, they're thinking. But I will tell you that I saw some data from the Parker Solar Probe. One of my colleagues was seeing radio waves that are coming from the sun out into a weaker field, and the radio waves make this like whistlers, like this, and you can, there's a lot of cool data starting to come in. It's going to go really close to the sun, the closest any satellite has ever got, and it has to protect itself and so on. So I urge you to ask David Malaspina to come and give a talk and tell you all about it, because it's really cool. Yeah, I'll give you that name. Don't let me forget. Right. Okay, so from the sun, center of the solar system, to the smallest objects out on the outer edge of the solar system. So what I'm going to do is to talk about the Ultima Thule flyby that happened on New Year's Eve, this past New Year's Eve. And, but I'll start off a little bit about Pluto, the main purpose of this mission. So if the sound works, we should get the launch. Maybe we don't have sound, but oh, what the heck. You all know what a rocket... You all know what a rocket sounds like. Oh, there we go. Thank you. Thank you so much.
Just 15 seconds. Everything continues to look good as the atmospheric movement climbs away from Florida's east coast. Our 5 solid rocket strap-on boosters are burning just fine, sending the New Horizons spacecraft on its way to the very edge of our solar system.
Excellent. Okay. Anybody here work for United Launch Alliance? Yeah. Great. Excellent. Yet again, fabulous launch. Really good. Cool. Okay. So we're on our way. That was back in January of 2006, such a long time ago. And we launched this small spacecraft. It's about the size of a small grand piano. It's small, not a baby grand, right? Quite small spacecraft. And we have a bunch of instruments. It's powered by radioisotope power system, plutonium, and produces about 200 watts. We have an antenna that, by the time we got out to Ultima Thule, it was a 6-hour one-way communication Think how long that is to send all the signal at the speed of light, the radio signal, back to Earth. And so this is a robot. You are not controlling this thing with a joystick, right? You have to tell it what to do, and it goes and does it, and then turns back and tells us what it did. And the transmission rate was 3 kilobits per second. Average phone is what, 50 megabits, something like that. You know, so it's a really small transmission. It takes a long time to get the data back. So let's look at the instruments. We have various instruments at different wavelengths. The Alice UV instrument was built in Texas, measures UV light. I'll talk a bit about that. Ralph wide angle and color, that was built at at Ball Aerospace in Boulder. Lorry, the long-range camera, was built at the Applied Physics Lab at the Johns Hopkins University in Maryland, as was Pepsi, particle data. The SWAP instrument, also built down in San Antonio, Texas. And we use the antenna to do radio experiments, and I'll talk a little bit about that. But of course, the most important instrument of them all is the student dust counter that was designed, built, tested, operated, and data analyzed by students at the University of Colorado in Boulder. So we've had a whole teams of students coming through. They really did have a good training. Many of them have gone off to become professional aerospace engineers or scientists. And what this is a piece, something about the size of a dinner tray. It's a bunch of plastic that's very sensitive. And as the spacecraft is barreling along at 30,000 miles an hour, he goes into the dust and detects, counts pieces of dust out in the outer solar system. So I'll tell you a little bit about that later. And they've just put out a new results status report at 38. This is a whole bunch of students who've come through and been trained, and they're now putting the data out, publishing the data.
So it's kind of like a Roomba, just collecting dust?
Collecting dust, yes, I see what you mean, yeah. Well, it is robotic, but yeah, just plastered, just to be geeky for once, just for the hell of it. I know you were making a joke, that's fine. But let me just point out that it sits here on the spacecraft, and so you keep the antenna pointed back towards the Earth, it's coming this way, right? So it's ramming through the dust and collecting it as we go through. Okay. So where are we going? Well, we're going out past the orbit of Neptune. We've gone past Pluto, and I'll show you a little bit about that. And this is the region called the Kuiper Belt, which is this region. Pluto was the first one discovered back in 1930. But the next Kuiper Belt was detected in 1992. So it was a long time, and these are pretty small objects that were detected in the Kuiper Belt. A few bigger ones, more like the size of Pluto, have since been detected. But it's the new frontier, if you like, or the third zone of the solar system, beyond the inner planets, the outer planets, and the outer edges of our solar system. So, tell you a little bit about the Pluto system that we flew past. Just before we launched the spacecraft, we knew that there was Pluto and a moon, Charon. And then just as we were about to launch, we detected 2 more moons, and then soon thereafter another 2, using Hubble Space Telescope and these little objects here that are all orbiting out further. And then we flew over Pluto and took these amazing pictures of this terrain. And it was just such a surprise. We have big mountains of water ice sticking up. These are mountains as big as the Rockies. We have ice that is nitrogen ice. This water ice over here has some impact craters. It has grooves. It has valleys. It's covered in this brown gunky stuff, which is slimy, oily stuff raining out of the sky onto the surface. This fresh surface is Tombaugh Regio, after Clyde Tombaugh, the discoverer of Pluto. And you actually have convecting ice here. There are icebergs, which are water icebergs, because water floats in nitrogen ice. And just a remarkable set of things to look at, diversity of terrain at Pluto. And this is my favorite picture. It just shows variety of terrain, mountains, plains of ice, and the hazes, all of this variety of things. I just thought there would be a single lump with a bit of bashed with impact craters. I never expected to see such a variety of terrain. So, doesn't that look like a planet to you? Dwarf people are people, dwarf planets are planets. It's big, it's got enough gravity to pull itself together to be round, and it orbits the sun. Why do you need more? I think what's good, actually, about this big hoo-ha about definition of a planet is it's got people thinking about the need to put a qualifier in front of the word planet. So, terrestrial planet or rocky planet, gas giant planet, dwarf planet, because they are small, So I think it's an interesting debate and discussion. Okay, let's move on. Now, when New Horizons went behind Pluto, we could look through the sky and see the sunlight behind. So this is sunlight, and it's scattering of sunlight just the way our sky scatters blue light. You get this blue around due to the haze in the atmosphere, which is really cool. And then, okay, time for the 3D glasses. We have snaky terrain. Now, you may want to wiggle your head around. I think that may help. Try. I don't know how good this is. Does it? Oh, it's automatically moving on. I can go back if you want me to. Is that one all right? Can you see it? Go back? Okay, I'll go back. Okay, sure. I mean, some people can't see it, and it's maybe not the perfect 3D, but it gives you some sense of what it's like. Yeah. So this is called snake terrain. We don't really know what it is. Maybe methane ice that's forming these sort of crusty surfaces.
How much is it exaggerated?
You mean the vertical relief? Well, this relief is actually thought to be, a few hundred meters. This is not a small, these are kind of big cliffs. They're not tiny. Wow. These are the size of the Flatirons, probably. Maybe that's a bit exaggerating, not quite that big, but, pretty big. Yeah. Okay, I'll go to the next one. Okay, so this is an overview, and I don't know how well I have a feeling this may not work too well in 3D. A little bit? A little bit. So you can see these grooves over here. Can you see these grooves? And then these big impact craters and the Clyde Tombaugh Regio. And the flat spot's really flat, right? Okay, now try this one. I think this is my favorite. And you really get to see the flatness of the glacier, and then the grooves of the stuff that's flowing into the glacier, and then the water ice, big stuff sticking up. Cool. Okay, let's move on. That's Pluto. Really great, exciting, and I think you've had a talk from John Spencer about Pluto. Then the idea was, well, we want to go and see if we can find something else. And this is really difficult. We only had fuel for about 2 degrees of propellant to move the spacecraft, the trajectory about 2 degrees. So that's 2 fingers at full arm's length, right? 2 degrees. And so we had to look in this direction. So we had to look in the direction of Pluto and try and find an object behind. Okay. Why was it particularly difficult to find an object in the direction of Pluto from Earth in this epoch? It's not low it's in a particular direction, which makes it difficult. It's the most crowded, or the center of the Milky Way, right? And so you've got all these stars, and you've got to find some little thing in that crowded field. So it's really difficult to find it. And we used Hubble a few times, and eventually in 2014 we found this one that was called MU69. And we decided it was within that 2 degrees, we'd go and check it out. And so just to give you a sense of all the objects that are out there. So here's Jupiter, Saturn, Uranus, Neptune, and then out here is Pluto. And there's a whole now classification of different kinds of Kuiper Belt objects. And I don't want to get too much into it, other than to say these Pluto objects, there's P for Pluto, these Pluto objects tend to be up a little bit from the ecliptic plane. So this is the sort of angle up from the ecliptic plane. And these objects here are all in resonance with Neptune. So they orbit twice for every 3 times Neptune goes around the sun. And the net effect of that resonance is actually to scatter them up out of the ecliptic plane up to higher inclination. So those are the Plutinos, and they tend to be a little larger, and they've been scattered. There are other objects, in particular these ones here, which are orange, of which MU69 is one, that have not been scattered. They're fairly tightly confined to the ecliptic plane. They're not in a resonant orbit, and they're thought to be particularly primitive pieces of the leftover pieces from the formation of the solar system. Now they're called cold classical to contrast them with the hot classical, which are these yellowy ones. And it's those darn dynamicists, the ones who had the cheek to demote Pluto. Why we listen to these dynamicists, you know, they're all like, ooh, well, these orbits all going around, blah, blah, blah. They call these hot, and they call these orange ones cold. It's got nothing to do with temperature. It's purely an issue of scattering, the amount of scattering versus unscattered. They're all darn cold. They're out on the edge of the solar system, like 40 degrees Celsius, absolute zero, or minus 233 Celsius. So they're all cold, but it's just an issue of how scattered they've been. Okay, hot means they've scattered a lot, cold means they haven't scattered as much. And the main point, that all I really wanted to show you here, is that these are very different objects in terms of their history, we think, because of their location in the Kuiper Belt. Pluto has evolved a bit, and look at that geology, all sorts of evolution clearly there, whereas we think MU69 is pretty primitive. Now for size, I did this demonstration. If you take an exercise ball, that's Pluto. And for comparison, MU69, or Ultima Thule, we later called it, is the size of a ping pong ball, okay? So you're now beginning to get a sense. Pluto was pretty small to start with, and now we've got this very small little object, about 25 miles across. Okay. So, what's this? Oh, here. So, we want to go look at it. Now, there's some really cool techniques that you can apply to looking at objects like asteroids and comets and Kuiper Belt objects. If you're here on the Earth and you look out at this body, there's a star, and if you're lucky, that star goes behind the object. And you can use star catalogs and go online and use all the tools and techniques that are available to work out when that star is going to go behind the object. And then what one wants to do is to put a whole bunch of observers in a range of places, spread out, say, 50 miles across, 20 different teams, and they all look with fairly small telescopes, you know, sort of thing that fairly modest for many of you, tiny for Jack. Jack, yours is huge, right? Yeah, right. Yeah, I know. And you use these to go look, but you have to travel to different parts of the world to do this. So these were all, these are a variety. I don't know where these places are, but anyway, they were looking at these things, and what you do is you see a dip and you work out the shape of the. This was actually just an online thing I did to try and explain the concept. So that's the concept. Now for MU69, there have been 3 major occultations, one down in South Africa and South America here, another one down in the Pacific, and then another one down in Argentina. And then there's another one that was in August that was in Senegal, West Africa. And teams of people were sent off to go look at these MU69 occultations. Here they are in Senegal, having fun. And here's an observation that was made in South America. It was July, but it's in South America, and so it's pretty cold. This actually is a guy who's undergraduate, just graduated, just about to start at CU as a graduate student, wearing my jacket that I lent him to keep warm. And there was a US ambassador came along to help observe, which is really cool. So this is a really great outreach activity. We have teams of students and professionals going out there with boxes of telescopes to observe, and then bringing in the local observers, the local school system, the local college volunteers, and so on, to make observations, which is really cool. Okay, so here is Mark Bowie from Boulder. He's at Southwest Research in Boulder, who got this all organized, a lot of work pulling this together, and he's so pleased that this third occultation had 5 chords that intersected MU69. And so these stellar chords going behind the object. And that allows you to get a sense of the shape of the object. Okay. Now, that helps us locate it because our astrometry wasn't very good. We didn't really know where it was very well. But using the stellar occultations helped us get its location as well as its size and some shape. But this is a really difficult, even harder than going past Pluto, because it's a lot smaller, as demonstrated by the exercise ball and the ping pong ball. We had a really closer flyby. We felt that we could get closer. And that's partly because we knew it would be a dim object and we wanted higher resolution. And so you've got to be careful about smearing and so on. So there was a lot of concern about how to do that. A lot of uncertain location. I mean, it was only discovered, right, in 2014, and it's barely moved through the sky. And so getting its location is very difficult. You can get its location across the sky relatively well, but how far away it is desperate, right? And so you're going to go flying by, and you can take your camera and go click, 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 and you're going to do all of across the sky, and most of those are going to be black, right? So you have to have some intelligence on board to first send down the ones that actually have something in the image, right? Don't send all the 0 pixels down, and then you can look at those ones first and then look elsewhere afterwards. We're down in spacecraft power. The plutonium-238 has decayed a bit, so the amount of power is down. And then, of course, this monster of a round-trip light time to communicate with the radio waves to the spacecraft. Okay, so the plan then was to go through a geometry like this. There's a shadow behind, and we wanted to, and this is the orbit, And here's the New Horizons trajectory going from the sun over above it, like this, looking down on the object. Okay, so now on approach, starting in September, we're looking at this with a raw image with the LORRI spacecraft, and it's beginning to get visible. This is, you subtract the stars to get the actual object. Oh, there it is, right? And that was December, right? So it was really small, and we were moving really fast towards it, and it was really hard to see it on approach. So this is a repeat. This is actually worth watching because it's kind of cool. If they didn't put the target around it, you'd have a hard time working out which one it was, right? But now you can see, and it's looking like it's a funny shape, but you're really not getting much of a sense of shape, even by getting right towards the end of December. So we had this plan. This is going to be the flyby aim point. We were searching for moons, didn't see anything, didn't see any rings, so we weren't so worried about debris or anything like that. We were all ready to go and try and get pretty close. So we were a little concerned about dust and gas. It's not very likely because it's so far away from the sun, so it's very cold. Most of the comet jets, this is Comet CG that the Rosetta spacecraft landed on, those jets tend to come out when it gets closer to the sun and heats up and starts spewing out stuff. And it's this tail of material coming off that when the Earth goes through that tail, we get your meteor showers, right? So that's actually what it is. If we went through here with Earth, we would get a meteor shower. Okay. So this was the plan. 2 hours to go right through, making all these observations with all the different cameras and so on and so forth. A big plan, get it all rehearsed, put all the data on board, and then turn back and tell the Earth that we were there. Now, the shape was a big question. From the occultation results, we sort of had a hint that it might be bilobate or have two pieces stuck together. Or it could be sort of like a potato or a eggplant or whatever potato or kind of vegetable you want, right? We weren't sure. And indeed, if you look at all the objects of various objects that we know that are out there, we were thinking about a bunch of craters, a bit like Saturn's moon, or it might be this sublimation, this stuff coming off when it heats up, a little less likely. And then this is much smoother, looks like it's been processed with heating up the surface of the ice. So we were sort of making guesses of what it might be like. Okay, so now we're beginning to get a sense with the actual cameras on board. What shape is it? You take a picture here with a few pixels, and then you cheat and fiddle, imagine what it really looks like, right? Image processing. And then it's getting even better. One day before, this was the best we'd ever had. It's kind of looking like two pieces. And this is the size. And then we know it's success. And there's, of course, the mission operations manager, Alice Bowman, the mom. It says everything's successful. The spacecraft's alive and it's gone through and we got data on board. This is Alan Stern from Southwest Research in Boulder, who was a graduate student at the University of Colorado, who persuaded me in 1989 when I first started at CU that we should campaign to get a mission to Pluto, and he ended up being the principal investigator of the mission. So another great success. Everything worked well, and we get our first picture. Look at that, totally cool. And yes, it's got two objects, a bigger one and a smaller one. They're pretty round. That's what it looks like. So you can see in one day, you go from this fuzzy, maybe 2 little bits, to a really quite well-defined 2 object, 2 pieces, bilobate. So for comparison in scale, this is Pluto, and this is Ultima Thule, right? So you can see how small it is, right? It is brownish, and maybe for similar reasons that Pluto is brownish, because of photochemical reactions and also galactic cosmic rays reacting with the ices and making hydrocarbons, brown, gooey, organic material that rains out of the sky in the case of Pluto, or is generated due to cosmic rays bombarding the ice in the case of Ultima Thule. Okay, for size, here's Boulder. Here is Ultima Thule, just to give you a sense. I've designed this for talking at CU, but you get the sense that this is a pretty small object. And for comparison, there's this really... Isn't that a great picture? It's great. Gives you a sense of scale, right? Yeah. So comet CG, I always call it. I can't pronounce that. Anyway, is a lot smaller. But look at, while we're looking at that, it is very dark. But look at the neck. It's 2 objects, but it's sort of really got very processed, that surface, hasn't it? It looks like there's been a lot of evaporation and then some dust coming back in and so on and so forth. When we look at the snowman, as we got to call him, you can see these 2 pieces are they're very round, and it's a pretty clear neck, right? It's whiter, and there's some big debates about whether that's fresh ice or whether it's just that when you get dust produced, that tends to be a gravitational low, and does it sort of like flow down into the neck region. But this clearly has not had a lot of impacts. There's a few impacts, but it looks like it was each was pulled together to make a sphere, and then the 2 spheres hit each other. So this is the very best picture that was ever taken. You can see we called the top bit Thule, the bottom bit Ultima. You can see a few impact craters. There's something here that looks like there may have been an impact crater that got eroded away, but you sort of have a feeling of each of these planetesimals were like a snowball that was sort of come together with pieces, and then the 2 snowballs came together very gently and formed, came together and were merged. And indeed, if you look at what was predicted by these occultations, the actual object is pretty close, right? So they really kind of nailed it, right? Pretty well. Yeah, pretty good. Yeah. Now, if we look at the color, this is the high resolution black and white, and then a lower resolution color. You put the 2 together, you can sort of fudge it and get a better...
Just jiggle the button.
Jiggle a button. Okay. I'm going to let you do it, because I can't get it to jiggle. Of course, now I'll... What did you... Oh, you did it that way. Ah, clever. Okay, good. You've done it. It's not rocket science. Okay.
Wow.
It is a laser. It is a laser. Who said that? I'll point it at you, right? Okay, so you can see the color, and this is what I meant about the idea of weathering, space weathering, we call it, where you have charged particles or high energy photons, radiolysis, changing the chemistry of the surface. And in the outer solar system, it tends to make things this sort of brown, gunky color. Carl Sagan invented the term tholins to sort of describe these products, which are photochemical reactions or radiolysis productions, where you have common elements, carbon, nitrogen, oxygen, hydrogen, a few things like that. Put them together, you end up with these sort of semi-organic or primitive organic materials. So these are the surface slopes. So this idea that the neck here could be produced by having two objects. This, by the way, is the spin axis. So they're spinning around that way, around the big one. And if you pull them together, what you find is that you get a sense of the gravity. So very stronger gravity here. So that's sort of like things falling down or rolling down a hill to the neck part. And so if you have touching spheres with the density of water, this is the gravity that you will end up in the neck. And that may be pulling in dust that gets generated by little impacts. So that's the idea. So here there's several ways you can do stereo. This is one way where you look from two different perspectives. It's not color yet. You get a sense of this shape by flicking between these two shapes. Now, Brian May, who's from Queen, anybody seen Bohemian Rhapsody? Oh, he's great. He's great. He's great. He's marvelous. He gave me a hug. Anyway, he came and hung out with the team, and really he's contributed. He's got a PhD in astrophysics, so he deserves it. He came and hung out with us, and he's actually speciality, I think, is zodiacal light, right? All the dust that's near the sun. But he's really interested in 3D, and if you have one of these fancy pairs of glasses, then you can turn this into a 3D picture, okay? He's got these fancy glasses. They're not these ones. They're a lot more fancy and expensive. But he came along and he made these images, and we talked about 3D and so on, and the geology and so on and so forth. Much easier is if you use this. And hopefully, this is a reasonably good 3D. Is that quite good? Does that work? Again, sort of moving your head around kind of helps a little bit. I don't know. Sometimes I think the motion back and forth helps a little bit. These online? Probably. Yeah, probably. I've lost track. Probably. Paul Schenk is the guy. He's at Lunar and Planetary Institute down in Houston, and he's the guy who makes these. But it's kind of nice to see the 3D nature. We didn't get a whole lot of different perspectives, so it was kind of high resolution pictures of these different perspectives, so it's not super clear. Okay, you done? You ready? You want to move on? Or you? Okay. Okay, so this was the sort of actual view, right? And you're flying over it, and you get these sort of views. It's spinning a little bit. And so this actually is a better one on the left. And now, when you just resize it so you don't get this thing hitting you in the face all the time, and you focus on the one on the left, you can begin to see that it isn't exactly round, these two shapes, right? The smaller one is pretty round, but the lower bit is kind of flattened, right? Yeah. Okay, so now we're thinking not like this, but more like this. And the spin axis is like this. Now, so this dashed line, I think, is sort of the range. It may be they went from this big round one to the flattened one, and then the next month they'll come out, well, it's actually kind of in between, you know, the way people, scientists tend to go, oh, it's this, oh, no, it's that, oh, it's this. Well, it's sort of in between. Right. So we'll see, but it's kind of interesting that it does look like it was a little flattened. So how do you think we made this? Well, you start off about 4.5 billion years ago with material in the outer solar system. And if it's all the way out there at, say, 30, 40 AU, it's moving really slowly, Keplerian speed around the sun. But occasionally they'll bash into each other or maybe come together. But if you have two pieces of debris that start spinning around each other and slowly coming together, you need some dissipation, coming together, and then slowly and eventually they come together. And the idea is they touch really slowly, so it's a bit like, you know, walking into a wall like this speed, right? And so they walk really slowly, and so that means they didn't break up, and they just came together, rotated around each other, and then merged. And maybe that neck is from where they got a little warm and merged together and melted a little bit. So that's the idea. And so they're pretty primitive. You know, if the formation of the solar system was 4.5 billion years ago, it probably got to this stage, I don't know, 4 billion years ago. So these are really old, primitive pieces of the solar system. We're getting a sense of the building blocks. So here are a bunch of other objects. We've seen now comets, all much closer to the Earth than Ultima Thule. And you can see that this is the largest of these. These other ones are much smaller and much more evolved. So you sort of get a sense that the surface has been a lot more evolved, right? This kind of looks a bit like the snow up in the mountains in the middle of summer where they've been ablated over a whole season of heating and cooling and heating and cooling. So this is the point I made about the cold classicals versus Pluto, and the idea is that comet CG got scattered from the outer solar system in, and many of these things got scattered and came in and either hit Jupiter, or pulled in by Jupiter, or scattered by Jupiter to hit the Earth. And it's this scattering of the Kuiper Belt objects that probably brought water into the Earth and Mars and Venus and so on, delivering water to the inner solar system through these things migrating, being scattered. But Ultima Thule is probably one of the leftover pieces. Now, I work on the interaction of the solar wind with various planetary objects. And for Pluto, we detected with the two particle detectors an interaction with the atmosphere, the escaping atmosphere of Pluto, which is the outer layers are methane. Most of the atmosphere is nitrogen, like the gas in this room. And we had an interaction with the supersonic solar wind, quite rarefied solar wind, and we detected this and made a sketch of the scale of this tail of material being carried away away from the sun. When we look at Ultima Thule, and I use the US again for scale, you can see how small Ultima Thule is and how far away we were. So not surprisingly, we didn't see any interaction. We were so far away, and probably what's happening is there's no real much of an interaction other than this stuff just blasts into it and hits the surface and causes this radiation changing of the surface chemistry. So pretty boring from a scientific viewpoint. We were just sort of sitting there twiddling our thumbs. We didn't get any special data. But we were enjoying Brian May and everybody else having a lot of fun. So that was cool. Okay, so no evidence of a coma or an atmosphere. It's too small. And too far away from the sun. No evidence of rings, no solar wind interaction, and no evidence for satellites. So pretty interesting little object, but none of the peripheral stuff around it that a larger object like Pluto has. So the data's coming back. It takes a long time. It'll take a total of 20 months if we get all of the stuff back. And so the data playback continues. And we're heading on further out. We're trying to see if there are more targets. We are using Hubble, but we're running out of the power of Hubble. We're going to try and use the camera on New Horizons to see if we can see some distant Kuiper Belt objects. There's probably not going to be anything that we can fly to because we don't have much fuel left. Before we only had enough for deflection of 2 degrees. I don't know what it is now, but it's much less than that. And so we will just try and take pictures as we fly through the rest of the Kuiper Belt. And of course, we will use the instruments to measure the solar wind as we go out and measure the dust and see where does the dust that's produced by the breaking up and bumping into each other of these objects, where does it drop off? Where is the edge of the Kuiper Belt? And then eventually we'll probably run out. We probably won't get as far as Voyager 1 and Voyager 2 that have left the heliosphere and are out in the interstellar medium. We'll probably run out of fuel on New Horizons. It's a smaller fuel source, and our antenna for communication isn't as powerful. And so sometime like 10 years, we'll be done. So with that, I will thank you very much. That's perfect timing.
I think that Ultima Thule is one of the primitive objects, right, that was out there originally. So the idea is that some of the objects, such as Pluto maybe and Triton, which is a captured moon of Neptune, as Uranus and Neptune, we now think were formed in close to Jupiter and Saturn. They ended up getting into these resonant orbits, of course, Uranus and Neptune to move out. Now, the reason why we think Uranus and Neptune didn't form where they are now in the outer solar system is they're moving so slowly it would have taken longer than the age of the solar system to accumulate their mass. So if you make them in closer, they end up in a resonant orbit with Jupiter, the big bully that sort of kicks them around, and they migrate outwards. And as they migrate outwards, Uranus and Neptune kick these icy objects in, and we think that's how we got water to the Earth, and maybe how the impact craters came to the moon, the heavy lake bombardment which we know about. So that theory, I think, still stands. There's some question about some of the details, but I think Ultima Thule just, in my mind, confirms, yeah, there was some of the stuff that was just out there to start with and stayed out there. It was not pushed around as much. Yeah.
What was some of the specific geology that they came up with the observations?
For Ultima Thule?
Yes.
Well, it's funny because it doesn't really look like a very geological body, does it? I mean, it doesn't have rivers and mountains. It has a few impact craters, and that's about it. And so it's funny to hear the geologists who are used to throwing all these technical terms about, they're like, well, it's a bit of a hole, you know. It's a bit unfair. I shouldn't say that. I can see the geologists going to jump on him. But the geology, I don't think is the right phrase to use for what you see on Ultima Thule. It's too small, and you know, yes, it's receiving a little bit of impact cratering, but it's basically surface chemistry due to radiation hitting the surface.
What is composition? I haven't heard anything about composition.
Composition, yes. Yeah, we do actually have composition measurements. It's water ice, methane ice, nitrogen ice, the usual ices, the common ices out there that I know of. I'm not aware of anything very exotic. Yeah, and I should have put that in. Yeah, but ice, and more ice with a bit of surface degradation due to the radiolysis.
Another question up there?
In one of the ending slides, you suggested there was no solar wind interaction.
Yeah.
What does that mean? What would an interaction have been? or should have been?
Well, you saw that picture I showed for Pluto, which was an atmosphere that's escaping from Pluto. It becomes ionized, photoionized, but because the gravity is very weak, it goes a long way, and the solar wind is weak, it makes it larger. If you took Pluto in close to the sun, it would be a much smaller interaction. And so there, what's happening, you've got ionized gases, in this case methane ice at Pluto, and then the solar wind, which is also ionized, carrying a magnetic field, interacts with those, the solar wind, the charged solar wind, and the magnetic field interacts with the charges of the escaping atmosphere. And so you end up deflecting the solar wind around. The thing about Pluto and these small objects is the magnetic field is so weak that the scales of that interaction are so large. And so it's not so much a fluid flowing around as individual particles that are moving. It's a much more kinetic process. Yeah. But with Ultima Thule, it's just more like our moon, where it's or an unmagnetized sort of chunk, an asteroid sitting out in the solar wind, and it just bangs into it. It makes a cavity behind, which eventually fills in. What do you call that?
If you've only downloaded a quarter of the data so far, do you expect some surprises in the remaining 75%?
So we had a big discussion about this at the science team meeting a couple of weeks ago, and there's a debate between, is there anything other than black images? No, or could there be the odd satellite, or maybe another Kuiper Belt? And there's a question about, do you expend the telemetry, very precious commodity out there, to send back every single image? Or do you say, look, let's go look over there and see if we can see, we think there's a Kuiper Belt object over there, let's use those resources to go somewhere where we know there's something to look at. And so there's a debate about that, right? And it's not clear. I think future missions, there'll be a lot more onboard data processing, a lot more pre-processing, and so rather than bringing back a big image that's not got a lot on it, each image will be labeled with the amount of actual information in it, and then so you won't bring down the things that don't have information in them. You've got more sophisticated ways of doing things like that. Yeah.
All right.
When was the last trajectory correction made? And I ask this because I realize there's a possibility that as New Horizons was going by, that you would get an end shot and not a full body shot. Yeah.
The trouble is that we were moving so fast relative to this small body that by the time we would have turned around to get a back view, it was just a dot in the distance. So we took, as best we could, those views. Remember, we're actually going over the top. You're going over the top,
right?
We do the best, and we actually have a really good sequence there.
Yeah.
But there isn't a whole lot of value in looking from very far back because it's just too piddly.
Yeah. So it was planned that way so that you would get the best look at it. Okay.
A lot of work went into that.
Okay, question over here.
Okay.
So, assuming this is it for New Horizons and there's nothing else to find, what's the next thing for Giants?
You know what Alan Stern's like. We're going to do this. We're going to do that. We're going to find this. We're going to do it. We will be writing a proposal to NASA, and NASA will decide: do we continue, or do we just make looking for Kuiper Belt objects, which will be harder and harder to do with the cameras? They'll be smaller and smaller and harder to see. Or do we just keep measuring the solar wind and the dust?
What I meant was, is there other missions coming up in the decadal survey that have constituencies that are going to someday launch someday? What's next?
What's next? Next thing is Europa.
Europa.
Right? So we're going to go see what that icy moon is like and whether or not there's any evidence of material coming from the ocean out, and we can detect what that material is. Of course, we all think it's whale poop. It's probably just And then there's a big push for Uranus and Neptune. I think that's going to be a big push. It's tough, but big.
Do
big
they have
goal.
any estimates or theories about how much time was involved, before the two objects merged and how it looks now?
Well, they had to have moved really slowly to get together, right? Because we know that they look like they were two round things that didn't get smushed.
But it looks like they're kind of getting, there's a lot of process involved with them kind of merging.
Yeah, the difficulty thing is we don't actually know the density, so we don't actually know the mass of these objects. So you can make some hypothetical guesses and you can do some modeling, which people are doing. But it's probably, once you've made these things and they're going around, it'll be on the order of weeks, I would guess, rather than minutes or many years. So I think that's probably once you have that dynamic start happening and then they can stick together. And because they're so far away out there and they're so small, that's it. They're done. They just sit there and rotate around.
Question up top?
Okay.
Do you have any sense of how likely of the population is, were we really amazingly lucky to get a very rare object that's bilobe, or are most objects out there bilobe?
Well, you look at all those comets, they sure a lot of them look like they're bilobe. Not everyone, but a lot of them are. And I think there is this feeling that in the process of stuff bumping into each other and that you do end up making bilobic objects. So we don't know the statistical numbers because we haven't got good enough observations. But people are saying, yeah, that's probably what I would expect. But they would, wouldn't they, say that that was what they expected. So I have to take it with a grain of salt. I think that's an important part of the Are there any women, any other women, or any other one woman asking a question? Come on, guys, there must be some women here who have a question. I'm trying to...
There's a young woman up there.
Anybody want to ask a question? Anybody? Not putting pressure, just in case. Okay.
All right.
You can ask me afterwards.
All right, and with that, we are going to adjourn to...
What do you want with the glasses?
Oh, please put
yes.
them back. I'll use them again at the next